Today we will do a few one-dimensional problems, okay? I'm sure you have seen them already in the course with George Thompson. I will just go through them because, I mean, it's essential to mention them. Make sure you really know what to do whenever you have a problem like this, okay? So it is probably partially seen, but still make an effort to be perfectly confident with this type of problems. They're mostly variations of the free particle. Free particle plus matching of wave functions. This is the game, okay? So let us start. We did already the infinite square well box, okay? So this problem. Either in 0L or sometimes a better choice of, I mean, an alternative choice of coordinates is, this is 0 and this is minus L over 2 and L over 2. Or you could call it this minus A and plus A, whatever, okay? Doesn't matter, depending on what you really want. This, we saw immediately that by confining the particle makes the spectrum already discrete, okay? While the free particle over all the line has a continuous spectrum, a particle confined in a region has a perfectly discrete spectrum. Let us see another problem where the particle is really not confined, although there is some step potential, okay? So let me draw better the potential. The potential is as follows. It is just a step, okay? So this is, say, V0, which we assume to be positive. If it is negative, it means that it's a step down, which is, well, closely related to a step up, okay? Okay, so let us see. Where should we look for? This is the energy, obviously. Okay, so the potential. Where should we look for energy eigenvalues? So we want to solve minus h bar square over 2m second derivative with respect to x of phi plus v of x equal to e phi. Plus v of x phi equal to e phi. Okay? Where should we look for e? Can e be negative, for instance? Huh? No, it cannot be negative because the minimum of the potential is this. And we said that the energy eigenvalues should be, okay, we indicated them with an n. Okay, we'll see what n is this time. The minimum eigenvalue should be not below the minimum of the potential. Okay, so it should be positive. You see immediately there are two regions here. The energy might be here, or it might be here. So above the step or below the step. Classically, a particle with this energy coming, for instance, from the left, bounces on the step and is reflected back, okay? While a particle which has higher energy goes through. So you see that physically these two cases should be different. However, certainly in this region, okay, the wave function is very simple, okay? How should it be? Free particle, okay? So the solution might be e to the I k x for a while. Let us assume that k is positive, okay? So k for me is positive. Therefore, this is not the only solution. There is another one. Which one? E to the minus I k x. Okay? Both of them are perfectly legitimate. Both have exactly the same energy. How much is this energy? So if you plug this here and you put that V is equal to 0 here, because this is 0, you will see immediately that E, which you can label now by K if you want, okay? We saw that K is a good label. E of K is certainly H bar square, K square over 2M. For both, okay? By the way, the fact that the wave function is real, the Schrödinger equation is real, you see there is no I appearing there, okay? Immediately implies that if a function satisfies it, the star of that function also is a solution, okay? So if a certain phi is a solution, then phi star is also a solution. The same thing would not be true if you have a magnetic field. If you have a magnetic field, then you know that there is a term P plus E over Ca square in the Hamiltonian. Have you seen this before? Classically, this is exactly what the magnetic field appears in the kinetic energy through the vector potential, and this is at the origin of the Lorentz force in the classical equations, okay? Quantum mechanically is the same form. Nevertheless, you see immediately that there is a term, okay, when you take the product of P and A, there are some subtleties about where P should go, what is the gauge of A, but let's go over them. The important point is that there are terms of this type, okay, which you see have minus I H bar, the gradient here. There is an I, an explicit I, okay? In other words, an equation with the magnetic field present would not be real. And therefore, you have to be careful. If phi is a solution, not necessarily phi star is a solution. All right? This is end of the digression. For our case, and you see, if this is a solution, the star of it, this is also a solution. In particular, you can always superimpose the two, A plus B, with two coefficients. Notice also, these are plane waves oscillating forever. So there is no question that you will be able to normalize them in any possible way with a finite normalization, okay? The only possibility would be to put the particle in a finite box, but this is not what is usually done in this type of problems, okay? These are so-called scattering problems, and usually you don't do what we explained last time, okay? You just work with the infinite space, and you simply do not impose the standard normalization square of the wave function integrated equal to 1, okay? Now, in principle, you could write a similar wave function here, okay? You have to be careful, however. Depending on the energy, the form of the wave function on the right of this step is different, okay? For instance, let us consider the case where E is positive. Then, let us rewrite this equation. I write in the following way. I write as E minus V of x, okay? Phi, K. Now, you see immediately that if E is greater than V0, then this is positive again. Exactly like it was positive here. So in the left-hand side, E was positive, and, okay? And we determined that it was related to K in this way. Now, in the second case, it's also positive what you have here. So you can solve, okay? But it's not E. It's E minus V0 that matters there, okay? So you have to solve the problem minus h square over 2m second derivative of a function equal to a positive quantity, which is now ek minus v0. Okay? What is the solution? With a different momentum, because now you want some, for instance, let us call it q. take the second derivative of something like this. When you take the second derivative, you get iq squared, okay? So this is equal to minus q squared e to the iqx. Then put the minus h bar square over 2m, and this becomes plus h bar square over 2m. You see, this quantity here now should be equal to this, okay? If you put k here, this would not be true, because h bar k square over 2m, you already wrote here, is just e, not e minus v0. So you see the momentum here is smaller, okay? So the other q has to be h bar square q square over 2m has to be equal to ek minus v0. Is this clear? Okay. So once you fix an energy, for instance, greater than v0, immediately k is determined by that energy, okay, through this relation, and immediately q is also determined by that energy. Once again, you have two solutions here, e to the iqx and e to the minus iqx, all right? And once again, you have two possible constants that you can put here, a prime and b prime, okay? So you immediately see that you have 1, 2, 3, and 4 constants to determine. An overall constant, you can rescale everything by an overall constant, because this governs the total normalization of the wave function, okay? Which is not going to be 1, and you are not going to impose it in any case, okay? So really there are 3 genuine constants, okay? However, you have essentially only 2 conditions to impose, okay? The condition is the continuity of the function and the continuity of the first derivative of the function. We saw it last time. So you see you have more constant to determine than actually condition. The reason for this is that, in fact, there are more than one solutions to the same energy. If you have no step, you see this immediately. For the same energy, you have both e to the ikx and e to the minus ikx, okay? It is for this reason that people usually do the following way. Rather than working with a general 4 coefficients, they do the following. They say, let me determine a wave function which is physically associated to the following problem. A wave e to the ikx impinges from the left on the scattering step, okay? A certain wave is reflected back, okay? The wave reflected back will have e to the minus kx form, okay? And I select this to be with coefficient 1, and this with coefficient r of k. R will stand for reflected part of the wave, okay? So I put here 1, or if you want nothing, and here r of k. And here, rather than having both of them, I just have a transmitted wave with generally a different momentum, q, okay? But only the transmitted part in this direction. So something like t, okay, e to the iqx. No incoming wave from this side. This might seem like unjustified at first, but it's not unjustified. As I told you, there are always 2 possibilities. And in fact, so just to make things definite, here I take a wave function that is e to the ikx plus r e to the minus ikx. And since everything will depend on k, I put a k here in this coefficient. And on the right, I write the wave function like that, okay? Now, by the theorem I told you before, the star of this is also a solution. But you see that the star of this thing is e to the minus ikx plus r star e to the ikx. And the star of this is obviously T star e to the minus IQX. Now, if phi star is also a solution, any combination A phi plus B phi star is also a solution. Okay? Well, which means that you can take this with a certain coefficient and combine with this with a certain coefficient. Well, you collect all the things and you will find a term for this and a term for this. On the right-hand side, when you take A times this plus B times this, you get a general combination of e to the IQX and e to the minus QX. So again, the most general form is really obtained. Okay? So you're not losing anything. You're just concentrating on a particular set of solutions, the ones that come from the left. Okay? There are other solutions that are the ones that come from the right, for instance, that you could also write. And the most general solution is a combination of both. All right? So nothing really. I know that this is a source of confusion, usually, okay? Because one says, but wait, why do I have to throw away here something and not here? It looks confusing, okay? But it's not. It is simply a choice of writing some particular solutions. Others are still possible, because the star is still, and the combination of both can be written. So the most general solution is of the form plus and minus, plus and minus. Okay? But since you see that you have a freedom in the constants, you cannot determine them all, okay? You just concentrate on these special cases and you do them separately. Okay? Is this clear? Okay. Okay, so let us do it. Let us do. Okay. Let us write the conditions here for this wave function. So to repeat, this is the psi on the left, and this is psi on the right. I still have to determine these two coefficients, okay? I'm not done yet. I know that given an energy, I can always solve this problem with this k and this q. But I want to know what coefficients I should put there. Otherwise, I'm not done. Okay, so let's see. The continuity of the wave function in the origin, so the fact that psi L is equal to psi right, requires something already. For instance, you put 0 here, and you get 1 plus r of k. And you put 0 on the right, and you get tk. So you see that tk and rk are related like that. If you have seen rk and tk before, you might possibly remember that in some cases, rk squared plus tk squared is 1. Okay? But you should remember that this is not always the case. This is true for a reflection and transmission in this case. If you have 0, you have some barrier, and then you have 0 again. Okay, you can do the same thing. So you write this as ikx plus rk e to the minus kx, and then you write here tk e to the I kx. You see the same k now, okay, because it's the same potential. Well, if you solve that problem, you will find that there is a relationship between this and this, exactly of the form you remember. And this is just a conservation of current. You can verify very easily that the current associated to this function is such that if you want to have the same current there, you must have rk squared plus tk squared equal to 1. Okay? We'll do it in a while when we switch to currents. Okay? The current operator, you remember what it is. Psi star, grad psi, minus grad psi star psi with some i's and h bars. Okay? So we'll do in a second. For the time being, just remember, not always this is true. Depends on the setting. Okay, so this is the first equation. The second equation has to do with the derivative being matched. And the derivative bring down ik. So you have ik e to the ikx minus ik rk e to the minus ikx evaluated in 0. And this should match iq now. Tk e to the iqx evaluated in 0. So you can drop all the exponentials because evaluated in 0 they give you 1 and write the equation ik multiplied by 1 minus now rk equal to iq tk. Okay, so you see that the I really drops. Okay? Very good. Now you can actually solve these two equations. So let me point out to the two equations. Remember, K and Q are given, so you don't have to do anything for them. They are just given by these two equations. And you have to solve for these two objects. There are two linear equations, so nothing could be simpler than that. Let me write for you the solution. You can verify it in essentially no time. The solution is Tk is equal to twice K divided by K plus Q, while Rk is equal to K minus Q divided by K plus Q. Okay? Okay, a few comments. Well, first of all, you notice that when what comments should I make? Let's see. When the energy becomes, for instance, very, very large, then, well, both the comments are really, not essential at this step. But it's more useful to make comments when the energy is less than 0. Okay? Yeah. Huh?
The energy is large and K is almost Q.
Right.
K would be 0.
Right.
That's transmission. Okay, Tk would be 1, which is
Right. Exactly. Yes. This is the comment I would make, but this is kind of obvious. Okay? When the energy is very, very large, R essentially becomes 0 because K becomes roughly equal to Q. You can neglect V0, okay? When A is very large. And so R is just 0. You get no reflection. If you have a tremendous energy, you are not reflected, okay? And everything is obviously transmitted. So this is the comment I wanted to make, but it's not, you can essentially read it immediately. It's more interesting to do the other case, where you will see it's less obvious. Okay, so let us do the other. So this is E greater than V0, what we have done here. So E this greater than V0. If E is less than V0, the situation K changes. It doesn't change as far as the left part of the wave function is concerned, but it changes for the right. Why? Because it's no longer possible to have a plane wave like this, okay? Because now E minus V0 is negative, okay? So you see it doesn't make sense. But there is a very simple solution to this. Well, one possibility is that you notice there is Q squared, and Q should be imaginary, okay? This at first might be a little bit puzzling, but there is nothing puzzling. If Q is imaginary, it's totally equivalent to having here a wave function that is now of the form e to the minus Q, okay, x. Okay? Obviously, there is also the other one. So if Q is purely imaginary, depending on its sign, could be e to the plus qx or e to the minus qx, where q is the modulus. And they have very different behavior. One is exploding, and one is decaying. Which one would you select? The decaying, not the exploding, right? For a very simple reason. The exploding one cannot be normalized. I mean, it's much worse than the plane wave. The plane wave has modulus 1. It's not normalizable because you are integrating on an infinite volume. Here, the probability of finding the particle far away is growing with the plus, okay? So it is very, very unphysical. It tells you that the more you go inside a barrier, okay, with the energy you have is less than the barrier. But the more you go to the right, with the plus, you would have more probability of finding the particle. Very, very strange, right? So in fact, totally unphysical. But this is possible. Notice that one never, yeah.
But is this always true? For instance, if our length scale is very small, even if we have some barrier, sometimes, we have such thing. We can take the one which goes e raised to plus qx. For instance, let's take a proton and a proton, and if the length scale is much, much less than the Planck scale, then we have
I see. He's asking things about scales which are subatomic scales, okay? And he is asking me if the statement that the plus is not acceptable is general or, strictly speaking, with the plus, you can go then to all scales, okay? And so the fact that for a while there is a solution that increases is not enough. When I write plus qx, it means increases all the time. And this is certainly not possible, okay? In subatomic physics, whatever, the wave function cannot increase forever exponentially. Now, on short lengths, that depends on the Hamiltonian and everything. But the simple problem we are doing here is two solutions. If you do it mathematically, both of them have, strictly speaking, second derivative, which is negative, no problem. So therefore, it matches a negative thing. But the one with the plus is very unphysical. The one with the minus is, in fact, very physical. It's an evanescent wave. Okay? Which means that the particle is able to get into the classically forbidden region, although with a probability that goes to 0 exponentially. Okay? So this is very quantum mechanical in a sense, because classically, obviously, you would not enter at all that region. All right? Okay, so let us do the same exercise. And the same exercise you can show it's very simple to prove, is that all it matters is to substitute, whenever you see Q, to substitute IQ, okay? The new Q. Okay, so the equations remain essentially the same, but now T of K is 2K divided by K plus IQ. So the Q that I'm talking about here, let me put a tilde, is this Q, okay? Which I assume to be positive, by the way. Yeah?
if both two particles exist at the right, we have two particles at the right.
We have two particles.
Yes, both particles with plus and minus sign exist. Can we are there symmetry?
No. The question is, if there are two particles, can I allow for both things? First of all, two particles will come towards the end of the course. Are they distinguishable, not distinguishable, identical fermions or not? They are bosons. There are many questions about the statistics, how they behave. But the single particle wave functions also have to have a physics behind, and it's not allowed that the single particle wave functions explode in this way. Okay? So forget it. I mean, those are bad functions. Do not even try to resurrect them with protons at very short scales or with more than one particle. I mean, to my knowledge, you just have to forget about them, right? Is this too bad for you to accept?
Maybe a particle and it's the particle.
Another department, another lecture room, okay? Not here, don't worry, okay? There are no antiparticles in this room. Okay, so I write simply now the solution corresponding to E positive, obviously, but less than V0, okay? Once again, you can calculate all the ingredients here. K, Q tilde, by the way, Q tilde is given by exactly the opposite thing. So it's V0 minus EK, which is now positive, obviously, okay? So you can calculate the ingredients in these two equations and tell me what is R, the reflection amplitude, and T, the transmission amplitude. And now there are a few comments that are useful. For instance, suppose that not the energy is less than V0, but suppose that the step becomes very, very high. So V0 becomes very, very large. Then, but first of all, notice this is a complex number divided by its complex conjugate, okay? So it's a number of modulus 1. The modulus of this is 1, because if you calculate the ratio of the two moduli, it's just 1. It's just a pure phase. So the reflection coefficient is just a phase for every possible V0. But if V0 becomes infinite, then you see that Q tilde becomes very large. Energy is fixed, okay? So K doesn't become very large. K is fixed, okay? This is fixed, but V0 is now here increasing, so Q tilde is just going very large, which means, by the way, that this is becoming extremely steep, extremely fast, because if Q tilde increases, it means that the wave function decays, which is obvious. The higher the step, the more you decay fast, okay? But you also see that this goes to 0. So transmission, if V0 becomes very, very large, goes to 0, like 1 over Q tilde. The reflection, however, is still of modulus 1. But notice, if Q tilde dominates and becomes very large with respect to K, you can essentially forget about this. And what you have is what? The I and the I cancel. The Q and the Q cancel. Just minus 1. Okay? The reflection coefficient becomes minus 1. What does it mean, minus 1 here? It means that in the limit V0 going to infinity, the wave function becomes this, which is a sine, okay? So this function essentially develops a 0 in the origin. It doesn't want to penetrate the barrier, I mean, if the barrier is obviously infinite, okay? So you see that you recover the boundary condition of the infinite well that we discussed last time. Remember, wave function going to 0. The wave function goes to 0 in the limit, obviously, because the two coefficients are 1 and minus 1, okay, in the limit. All right. Is this clear? Okay, let us calculate, just for fun, currents, because then this is useful in this exercise as well. Let me erase a few things here. I told you that if I have a certain wave function, I can calculate a current associated to it. In general, it's a vector, but in 1D, it's just one component. So I have something like I h bar over 2m. I forgot the sign in front. I think it's plus I. You can probably rapidly check with your notes. Huh? Then I have psi star grad, so the derivative of psi, minus grad psi star psi. Let us calculate this function. For instance, for this object. Okay? So here I should put e to the I k x plus r. Let me omit the k in the r. E to the minus I k x. I take the gradient of it. The gradient is I k e to the I k x. Okay? And here is minus I k r. So minus r e to the minus I k x. Okay? So this is the gradient. Okay, here, this is the star of that. So it is e to the minus I k x plus r star. R and t are generally complex, okay? Don't take them to be real. R star e to the I k x. Okay? So just do the multiplication, and you will get, in principle, 4 terms, right? There are terms that are constant. For instance, e to the I k x times that is a constant. E to the minus kx times that is a constant. So let's write them. They are I h bar over 2m. Then I have ik in front, coming from this. So I put it here, ik. Then I have this times that is 1. And this times that is minus r modulo square. Okay? These are 2 terms. Then I have 2 other terms, this times that and this times that. These are uglier, right? Because they have e to the 2ikx. Let me write them. So it's plus, for instance, r star e to the 2ikx. And here I have minus r e to the minus 2ikx. Okay? Very good. So this is from the first. Then let's do minus this term here. You see, this is essentially the star of that. Okay? With a minus, however. Okay? So let us take the star of this term and let's subtract it. Now, if I take the star of the first term, I get a minus I, but then I have to subtract, so I get a plus. Okay? So this term actually receives a factor 2 when I subtract that. On the contrary, if I take the star of this and I subtract it, okay, I get r did I make ik is there. I made, okay, ik is here and ik is here. Okay, now it's better. So if I take the star of this now, okay, which is minus ik, I subtract it, so it's with the r. So, okay, let me write it. It's minus ik r e to the minus 2ikx. I have to subtract it, which means I put a plus. And you see it's exactly the opposite of this term. Okay? So this and this cancels. And again, the star of this is plus ik r star e to the 2I kx, but I have to subtract it, so I want to put a minus, and it is exactly that. Zack, 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 zack. Okay? So you see the oscillatory factors cancel. The uniform term doubles. Okay? Is this clear to everybody? Very simple calculation, nothing really mysterious. So I erase this parts, and I just collect now the thing. The 2 goes away. I and I becomes a minus, okay? And which I think is wrong here, okay? This is the way to really check, okay? So it's the result here, if you just collect everything, is h bar k over m times 1 minus rk squared. Physics. H bar k is the momentum. Divided by the mass is the velocity, okay? Which is very reasonable. The current is associated to a velocity. In electromagnetism, you usually have a current density associated to velocity times a charge, okay? But here there is no charge. This is a number density, number current, and no charge current. So E is not there. All right, so velocity, that is fine. 1 comes from the wave that is going to the right, okay, from here. Okay? So this is associated to a certain current, V, P over M. The other one is the opposite wave. You see, it has a negative sign. Physically, it means negative current. And the amplitude is diminished by rk squared. All right? So, well, because that is not with coefficient 1. It has a certain amplitude r, and the current, therefore, has r modulo square, and with the opposite sign. Okay? So it makes sense, right? All right. If you go and look now, for instance, in this case, to this one, to the current here, you can do a very similar exercise. You realize immediately that the current here on the right should be what? Tell it to me. H bar Q, because this is the momentum, divided by the mass, times Tk modulo square. Okay? So you see, we learned one thing. We said that whenever a state is stationary, so the derivative of P of x and t, we know in general that is related to minus the divergence of J, always. Okay, this is true. This is a continuity equation. If the state is stationary, so it's a solution of the Schrödinger time-independent problem, then this is not there, which means that this is just 0. Okay? So the current has 0 divergence. In 1D, this means minus the derivative of the current should be just 0. In other words, the current should be constant in space. You see, it's constant on the left and equal to this. Okay? Therefore, it should be constant and equal also to this, which is the value on the right. And therefore, you see immediately that Tk is not equal to 1 minus Rk because of these factors k and q. Okay? However, if you are in this situation, okay, here the function is again Tk e to the ikx. Okay? And therefore, here I have again k. And in that case, therefore, t squared is equal to 1 minus r squared, which means the famous formula, sum of the square of them to be 1. In both cases, the basic principle is conservation of probability, which is reflected in this fundamental continuity equation and in the fact that the current is constant everywhere. All right? So please don't be too fast in concluding about R and T being given by a certain thing. By the way, you can verify with R and T here, okay, that this equation is exactly satisfied, obviously, okay? It's just a confirmation of the equations. All right, what else can I tell you? Okay. Just a short mention. With this R and T, you can construct also, you can construct at least two matrices. One is called the transmission matrix. For instance, let us look at this problem. It's a barrier. By the way, I didn't specify what the barrier was. I mean, it is true in general that the wave function here should be 1 plus R e to the minus k. And the wave function here should be some t e to the iqx. And obviously, you can in principle find the relationship between this and that. Sorry, a relationship is obvious, is the sum of the square equal to 1. You can find R and T also separately. Obviously, to solve this problem, what you have to do is to match this wave function to a wave function here, and then match this wave function here to the wave function there. So it's a complicated problem depending on the barrier. If the barrier has a strange shape, you should solve the Schrödinger problem with the strange shape inside and match the wave function to that. It can be difficult, all right? But in principle, there is always a certain R and a certain T that satisfy everything, all right? For certain cases, you can do the calculations. For instance, and this is what we are going to do next, you can do cases like this. A square barrier or a square well, which are somehow very related, okay? Both cases admit finding explicitly R and T by just doing simple calculation, because you have to match the wave function here to the wave function in another region with a flat potential, but careful, the Q is different from K, and matching again with the final V equals 0 problem, okay? So is it clear what you should do in principle? We're going to do most of this, okay? What I was willing to tell you is that there are at least two possible ways of describing what happens to a wave to the right of a barrier, for instance. You can write the coefficients of all, maybe I should just avoid mentioning this, but I mean, you probably have heard about scattering matrices and things like this, okay? R and T are the two basic ingredients that allow you to write a scattering matrix, okay? But it's not important for our discussion now, so I better avoid making more confusion than necessary, okay? The other thing is that you can also do the problem reverse. So you can try to do a problem where you send a particle from the right now, and therefore, how should I write this? E to the minus q plus some r tilde e to the iq. And you try to solve for a wave that is here transmitted, t tilde e to the minus I kx. You see the signs that I have chosen? They are different, okay? They correspond to a different way of writing other solutions. So this is the wave that is impinging now on the left. The wave that is reflected is there. It goes to the right. And here, the wave that is transmitted is this with the minus now. I put T tilde and R tilde because there is, in general, no guarantee that they are exactly R and T of the thing before, okay? So depending on the problem, there can be simple relationship between the solutions coming from the left and the solution coming from the right, or not. One possibility is to, why don't you try to do this? Okay, it's essentially the same exercises, but with a different way of looking at it, and try to solve for R tilde and T tilde. By the way, once you have two solutions, okay, so for instance, for this energy, you wrote this solution and the other, you can mix the two. And then, Obviously, you have all possible plus and minus there. All right? So, which makes you feel comfortable with the fact that there is no, because I mean, the setup looks unsymmetric. Huh? In one region there is only one, in the other there are two, and you are probably puzzled at first. But I mean, I try to explain to you that there is no puzzle. It's simply one choice of solution. The other choice is this. Do this. You can mix them if you want, if you really like. Okay. How are we with time? Well, pretty slow. I'm going slow, I realize, okay? Especially because some of these things you have seen. You never say this, obviously, because in this way I waste more time. But I know that you have seen these things. But nevertheless, I think it's a good occasion to revise everything and never assume too much, okay, from our young minds here, okay? All right, so let us do a slightly more complicated problem now, which you have seen, I know. So I shouldn't do it, really. It is the famous square well. Now, the potential now is the following. I wonder if I do... okay. The potential is as follows. This is the square well and not the square barrier. You could do with a similar procedure, in fact, by changing the sign of a few things, the square barrier, okay? I will comment on this. So let us take the potential to be 0 everywhere except in a small region of space between minus A and A. Notice that I now choose a more symmetrical setup than in the infinite square well. In that case, it was actually simpler to do things in 0L because, after all, the sign of kx is immediately an obvious solution for x going to 0, and therefore you don't have to distinguish between sine and cosine, and life is simpler in some sense. In this case, on the contrary, the solution has an obvious symmetry, the thing, which we are going to use heavily, okay? The symmetry of the potential is what? Is the fact that the potential is even under, well, with respect to the origin, okay? So V of x is equal to V of minus x, okay? Even potential. Obviously, if you change x into minus x in the Hamiltonian, nothing changes. The second derivative doesn't change, certainly, okay? So, in fact, this symmetry, x minus x, which is called parity, we'll study symmetries more in detail later on. For the time being, I just try to use them, okay, so that you will see examples when we do the theory of obvious realization of certain symmetries. Okay, so this parity is a symmetry of the Hamiltonian. The Hamiltonian is even globally. However, you shouldn't be fooled by the fact that the Hamiltonian is even to think that the solutions should be even, okay? The solution might be even or odd. The important thing is that they have to have a definite parity, either even or odd, not undefined parity. So the solution cannot be a mixture of even and odd. It must be either even or odd. All right? Obviously, if there is non-degeneracy, which is always the case in this one-dimensional problems. Okay? So this symmetry will simplify things considerably. Let's see why. So this is 0. This is, let me call it minus V0. So for me, V0 is positive. Okay? V0 I assume to be positive. The other exercise would be the barrier, okay, where plus V0 is the value of the potential inside. But let's do first this. Okay, so you realize that now there are three regions of space. The region, say, 1, the region 2 inside the well, and the region 3, which is here, to the right of the disturbance. Okay? So, energies, where should we look for them? Not here. From here up. But here, if the energy is here, you see the particle is essentially free here. Okay? So you suspect again that there will be a continuum of possible values. By the way, last time in the previous exercise, we never found quantized value of the energies. You realize that, right? E was any possible values, and K was therefore any possible value, not quantized values. This is general. Extended states, they are associated to a continuous spectrum, no discrete condition. All right? So here E can be any continuous value. On the contrary, here you see E is probably subject to some constraints. Here we will have certain finite number of bound states. Okay? So I anticipated here I should have a discrete part of the spectrum. And from 0 on, a continuous spectrum. All right? Now, let us do first the, for instance, the positive E case. Now, what about the wave function here? For any E, I can write e to the ikx and e to the minus ikx. Once again, let's take k to be positive for definiteness. Okay? So that these are obviously. But those are two possible independent solutions, and I can mix them. A plus B. Okay? What about the function here? Well, once again, let's see if I use some particular notation. Not really. I don't know. You have two solutions, e to the ikx and e to the minus ikx. Two possible things, C plus D. Okay? What about the solutions here? Well, for every E, now there is a new wave vector, okay, associated to what? To the fact that h bar square q square over 2m is equal to E plus V0. Okay? So you see it's higher energy in some sense. Okay? Notice the potential appears, so let me write it. Second derivative. If I bring the potential on the other side, I have V E minus V. But I have selected the potential here to be minus V0 because I want V0 to be a positive number, okay? And this is the reason why here I get E plus V0, okay? So in this region is e to the iqx and e to the minus qx with two more, say E and F. So you see total 1, 2, 3, 4, 5, 6, okay? Numbers of things proliferate. Now, 6 constant, and by the way, well, 1 overall constant is the usual normalization that we are not going to impose because these are not normalizable states. Okay, so 1 less, still 5. And then I have 1, 2 conditions here, 3, 4 conditions there. 5 things and 4 conditions. Usual thing, more freedom than constraints. Why? Because you have 2 solutions. Okay? In all possible cases like this, these are like the plane waves. You can always have e to the ikx or e to the minus ik waves. Degenerate. No way that you can have only one. All right? Whenever this happens, you have more coefficients than equations. in the previous case, we remedied to the problem by just looking for those particular solutions that were impinging, reflected, and transmitted, okay? Which you can do on both sides. And this had exactly the right number of unknown to be determined exactly. Now, obviously, we could do something like this, okay? But another possibility, especially when you work with the bound states, because if you now want, for instance, E negative, you have here a solution that is E to the okay, forget, let's not mix too much things, otherwise. Okay, so once again, here, the root is to describe things with less constants by just selecting, for instance, here, 1 plus R, okay, K, and here, rather than both, Tk. Okay? Let's count now the number of unknowns. 1, 2, 3, and 4. Okay? How many conditions? 1, 2, 3, 4. Perfect. Okay? So you can determine in principle R and T, and obviously E and F in normal. Obviously, you can do the other case also. So the wave impinging from there, reflected there, and being simply transmitted there. So the second solution comes from that. Okay? But we are not going to do both of them. In fact, I think that I will leave to you this case as well. Okay? I will concentrate more on the bound states, at least for today. What time is it? But we don't have too much time. Okay? So let me do the other case. E now negative, but greater than minus V0. Here. Okay? So case, say 2. Case 1 was E greater than 0. Now, let us see. How would be the solution here? We learned it must be an evanescent wave, right? So something like E to the minus, let me call it K. You see it's a kind of calligraphic K, X, not to be confused with this K, okay? So this is the quasi-momentum, I mean the momentum of the evanescent wave. So it doesn't oscillate at all. Obviously, in principle, there is some constant. And here on the, so let me call it B, for instance. And here on the left, I have what? A similar evanescent wave with this time the same K, but a plus here. In other words, I'm going here towards minus infinity, and therefore the evanescent wave has a plus here. Okay? With another coefficient A. In the middle, similar. Okay? But since I have no longer used C and D, let me call it C and D. How many equations? Well, how many variables? 1, 2, 3, and 4. You have, obviously, conditions here and conditions there. You could do, in principle, the full work like that. However, there is an even simpler way of doing this problem by exploiting parity. You will learn, and we'll do it in more detail later on, that whenever the Hamiltonian is even, the solutions can be of two types. Phi can be even or odd. Both. So let us look separately to solutions that are even or odd. Okay? This simplifies the problem considerably. For instance, if the solution is even, it means that A should be equal to B. Right? Okay. You realize why? Because you change x into minus x, and the same coefficient should appear. Right? If the solution is even, then C and D also must be the same. Okay? In such a way that this becomes a cosine of qx, right? So in the middle I have c times the cosine of qx, which is obviously even, and on the left, on the right, I have a e to the kx e to the minus kx. Okay? Now I have two variables, a and c, and I can just impose one condition there. Okay? All right? So this can be done. Let's see. Let's see if I have done this. Yes. Okay, so let's do this problem. The other condition is similar. In the odd case, here I have a minus, and here I have also a minus, and therefore I have sines rather than cosines. Okay? So the two can be done in a similar way, but let's do the even case first. Okay, so by the way, once you have determined that you work with even or odd solutions, obviously, once you impose the continuity there, automatically everything is fully respected on the left. Okay? So you don't have to do the work twice, in other words. You just match the wave function here, because then the wave function is even, and therefore it's perfectly nice also on the left. All right? So this is the way you cut the work in two, in other words, okay? Which is not trivial when you have a system of equations to solve, okay? Rather than having 4 variables, you now have only 2, which is much, much simpler. Okay, so let us find the solution. Impose the continuity there. So psi at, sorry. I should have been more careful. I'm calling A too many things. A is the position where the discontinuity occurs. Okay, so let's work with capital letters here. Otherwise, we start making confusion. I call B this. Okay, so this is B. Okay, so let me write the continuity psi at A on the, say, region 2 is equal to psi in region 3 at A. So this implies immediately what? The fact that A e to the minus k A is equal to B times the cosine of QA. Once again, Q is this, and K is okay. E is negative, okay, and therefore minus E is positive, and K is exactly this object. Okay? Yeah.
This B is B prime, right? Twice of...
Yeah. Call this B over 2, so that this becomes B. I mean, okay. So now the derivatives. Psi prime at A equal to psi prime at A in the two regions. When I take the derivative of this, I get minus Ka, and then I evaluate it there, and so I get this. When I take the derivative of the sine, I get minus QB times the sine of Qx, which evaluated at A gives me that. Okay? So these are the two equations. Once again, K and Q are uniquely associated to the energy by these two formulas. So it's like they are related, and it's like having the energy there. Energy, which I anticipate is not arbitrary. We will try to fix what is the condition on the energy. And A and B are those two constants. First of all, let's do some. Let us take the first, okay, and divide it by, sorry, the second, for instance, and divide it by that. By the way, here the minus is really irrelevant, right? So this divided by that is just K equal to, you see that B goes, and A also goes, and I have here a Q, and the tangent, sine over cosine, the tangent of QA. A and B have gone. By the way, it's only A over B that matters. Does this surprises you? You see, I mean, once, for instance, once you find what K and Q are, because this is now the fundamental equation to satisfy, and you realize that K and Q are both related to the energy, but now they should be related one to the other, which imposes a specific energy. Okay? Otherwise, they are not related. Okay? So, but once you have fixed K and Q, you can find, for instance, A over B. A over B is equal to cos QA divided by e to the minus Ka. Okay? So the ratio. Not A and B separately, because you can always normalize as you wish. For instance, by imposing that the norm is 1. All right? Okay, so the crucial thing to solve is this. The other is trivial. I mean, it's just a consequence. How do we solve this? Well, K and Q are not two arbitrary things. They are related to E. Let's try to do that. And I warn you, this is a place where you should start using dimensionless things, okay? So first of all, for instance, here I have Q times A. So let's multiply everything by A. That's not a bad idea, because after all, these are momenta, and Q times A is dimensionless, which is good, okay? In fact, let us write this, okay, as 2m over h bar square, and this as 2m over h bar square. And now I put an a square there, okay? Here. Okay? So you see that I have here a quantity that is, for instance, a k, which is the square root of minus 2me over h bar square a square. And similarly here I have a similar object. Notice that this object here is minus k square. Okay, so you can do some manipulations of this thing. But the important thing is now I have essentially a k on this side that is a function of the energy, and a q on this side that is also a function of the energy, and I should solve this problem. Unfortunately, it is not an algebraic equation. It involves a trigonometric function, so it's going to be difficult to do it analytically. Nevertheless, the standard trick in this case is to proceed graphically, which already tells you where are the solutions to be expected, how many, and then if you really want to know the numbers, you usually have to resort to some computer to calculate the zeros of the graphical pole. Okay, so let us simplify this a little bit. For instance, I can write this as A divided by AQ. So K over Q is equal to the tangent of QA. So let us see, what is the ratio of K over Q? This is equal to this divided by the square root of this. So it's the square root of minus 2m a square over a square e divided by 2m a square h bar square e plus v0. Okay? Now you see that really all these objects are unneeded. They just make confusion, which is good. Okay? So this thing here on the left is equal to the square root of minus e divided by e plus v0. Okay? And you could re-express. I think I'm making things more complicated than they should be, but this is always the case when you essentially try to improvise something, which is good, however. Okay, so you realize how improvisation sometimes can lead to, false ways of doing things, or there are optimal strategies that one does not uses. Okay, so let us do it together. This function here, tangent of QA, as a function of Q, how does it look? It looks like this. Okay? This is the tangent. Obviously, when QA is equal to how much? Where does the tangent explodes? Pi over 2, okay, minus pi over 2. And then it repeats, okay? So here I have, again, another branch. And again, oops, I'm not particularly nice drawing, which makes life more complicated. Okay? So again, this is the 0 in pi, and this is 3 pi over 2, and the same thing on the left. Okay? So this is this object here on the right. And now I have K over Q. How can I write K over Q here? How can I draw the function K over Q? Express everything here in terms of Q. Can I do that? Of course I can, right? Because K is a function of Q, if I want. So K, this is one possibility of writing things, but you can also write K, let's see. Let's not lose our lucidity, okay? So K is equal to a square, K square is equal to minus, so this object is equal to, so minus, this one I bring on this side, and this equal to 2m over h bar square a square v0 minus a square q square. Is this right? Roughly. Okay? So this is equal to a square q square minus 2m over h bar square a square v0. Okay? we are on the right track, because now I can divide here by q square, okay, or a square q square. So I take here a square q square, and here a square q square. And I can now take the square root. So you immediately see that k over q is the following function. It is the square root of 1 minus 2m over h bar square v0 over q square. Or if I want to still plot things as a function of q over a, I might include now the last q square, I promise, the last a square of this discussion. Okay? So one other possible way of writing this object here is this. This is better than this, in fact, okay? Because I can now plot on the same variable qa, and you see immediately that this is a function. Oops. There is something strange here. Did I make some? Huh? Where to the, I have no, it's minus and plus. Where is the, what do you suggest here? I should revise my algebra. Huh? Too many things. Write the right minus. Okay, too many suggestions. Either I do it again or you give to me the solution.
Okay, when you add the two brackets here.
Yeah?
Yes, they remain on the same side, but this one cancels.
This one cancels?
So
yes. And this
is positive.
So,
So when this one crosses, this is minus, this is positive.
So the sum of k square and q square is just with v0, and therefore positive, and therefore I have some mistake here. You are right. So I made, so this is a minus probably, and this is a plus. Okay, good, thanks. Okay, so this is now a plus, and this is a minus. Good. This is much better. I feel relaxed because no, it's a fundamental difference. When q goes to 0, so close to this region, that k over q does like following. Let me draw it with a different chalk. It does something like this, right? Because it's essentially 1 over q. So it explodes. And then when well, at a certain point, however, that function, okay, reaches the 0. Where does it reach the 0? Well, you have to equate, okay, this object to 0. So there is some point, okay, and this is equal to 0, which is, if you bring the 1 there, so when 1 is exactly equal to 2m h bar square v0 a square times qa square. So when qa square is exactly equal to that. Okay? So depending on v0, I have some value where this reaches 0. For instance, suppose that v0 is pretty small. Then chances are that the solution, that equality, occurs exactly here. So what you do is you draw your k over q, okay, this way, this green line here. So this is the left-hand side of the graphical equation. The tangent, the white things, are the right-hand side. where are the two equal? Here. There is only one possible value of Q, and correspondingly exactly one value of K, and correspondingly exactly one energy where the two match. Okay? This corresponds to a bound state, an even bound state. Remember, we are doing the even solutions. Okay? So only one even solution is present. But one is always present. You see, because of the divergence of this thing, this is always going there, and so it must cross the tangent before it goes to 0. All right? There's no way it can avoid hitting the tangent. However, if you increase V0, this can go here, but it can also go here. So another possibility is that V0 is higher, and you get to here. If you get to here, you have two solutions now, 1 and 2. Two bound states. And if V0 increases again, you can have the third tangent would be here. Okay? You can have even 3 because you just do like that. Zack. Okay? So this is always this function here. Is this clear to everybody? Is it? I mean, the algebra, there are plus and minus that can be dangerous, but once you do it, it's pretty simple, okay? So it is a trigonometric equation that you have to solve graphically. The right-hand side is a tangent. The other is the k over q, which you can re-express. Another way of writing this is that essentially square root of q square. So something, the square of this minus q square a square divided by q square a square. Okay? And you see that when this object becomes equal to QA, you get the 0 of the square root. If this is smaller, then you have essentially the denominator winning, and you have this divergence there. Okay? So in this way, you can find the number of zeros by increasing the depth of the potential V0. And you can also, I mean, you can do the calculations. They're very, very simple, and see that, well, they are related to the, for instance, suppose that V0 is very, very large. Let's see if we can do the calculation for V0 very, very large. What happens if V0 is very, very large? Yeah. But this function here, it's up in the sky, right? And therefore, where does it cut all the tangent? The question is, if V0 is very, very large, you see here, essentially this is I mean, large. And so you can draw it up here in the sky. It touches the tangent exactly at the points here, 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 okay? So you can immediately determine that the solutions are for instance, QA equal to pi over 2, QA equal to 3 pi over 2, and so on. What solutions are these? The infinite well solutions. You can verify immediately that these are exactly the even solutions of the infinite well problem. Okay? The energy is related to the q square, blah, blah, blah. Okay? There is an unfortunately shift. Here V0 is negative, so it becomes a minus. So the energy should be counted from the bottom, okay? Which makes the V0 appearing here. That is unfortunate. But they are exactly the same solution of the infinite well. The other part of the thing, but I think we have to stop here, is when you have an odd solution. The algebra is very similar, and therefore you can get similarly misled by the minus sign, except that wherever you had the cosine, now you have a sine, and that's it, okay? So something changes. For instance, here, the derivative of the sine, here I had the minus. Here, when I take the derivative now of the sine, I get plus QB, the cosine. Okay? So you see the minus is no longer cancelled. So you get an extra minus, and you also get, if you take the ratio of this over this, you also get cosine over sine. So the other equation is K equal to minus Q, the cotangent of QA. Okay? It's very, very similar. It can be done in essentially one line. So notice the extra minus and the cotangent in place of the tangent. So if you just do the usual thing, K over Q, this is the new equation. Now you see that where you had the tangent, now you have minus the cotangent. If you draw it, you will notice, well, I should now draw the cotangent past the end of the essential lecture, so I think you will never listen to what I do. But if you try to draw it, for instance, the cotangent has a, let's see, where are the zero? The zero is where the cosine is zero, is just shifted, okay? And you will notice that the solutions are just in between the even solutions, okay? So try to draw the new function, the cotangent, and verify that the new solutions is just in between the ones you had before. There are cases where there are no odd solutions, okay? So there are cases where the cotangent is not is just missed by this line here, okay? You don't cross it. So there could be just one even solution and nothing else. But before you reach to the two things, you will get the cotangent in between, okay? So it could be one even and one odd, two even and one odd, two even and two odd, and so on, in alternate order, okay? So please try to finish the graphic construction to verify the statement. All right, and also try to do the scattering problem that associated to positive energies. Okay, so I think if there are no more questions, this is enough for today.